Hi, everyone. Welcome to another presentation by Women Who Code San Francisco's Algorithms and Interview Prep Night. Tonight we have our mentor, Krys Flores, and she's going to give a presentation on trees with a focus on depth-first search and breadth-first search. Thank you so much, Krys. Take it away.
Thanks, Elaine. Alrighty. So, thank you to all of you who voted in the SF Algos channel. There were a lot of different topics, so I'm going to kind of skim over breadth-first search, and I'm going to focus on depth-first search because based off the input, people were like, "Oh my goodness, this one's a hard one. Let's focus on this." So that will be the focus. Though I will go over breadth-first search a little bit. Alrighty. I have a cheat sheet for today. Like with the last one I did for dynamic programming, I kind of put together a list of information about trees. So we're going to go to that real quick. It has information on what's top down versus bottom down, BFS, DFS. It also has a lot of examples of how you actually do each one of these. So this is how you would do an iterative solution on a binary tree for levels. This is how you would do it for an n-ary tree. In addition to that, I also wanted to make sure that each section had example Leetcode problems. So these are links to first the actual Leetcode problem and then my solution to the problem. And some of them have multiple ways of doing it. If my solution does not link to something, because like this, that means that I probably spelled something wrong when I was linking it. So just go back and go to my section that says practice and then Leetcode Python, and you will be able to find the solutions to those questions. So let's now go back to this. Oh, also, I should probably show this. So I have a summary at the bottom about when to use breadth-first search versus depth-first search. And then I also have some summary diagrams. You see the binary tree one everywhere, but I had more trouble finding the n-ary tree. So I just made those ones. So hopefully these could be helpful to you as you are studying. And then, oh, 1 second. Trying to, there we go. All righty. Okay, so first thing, depth-first search. So this is generally think about depth. You are going down. There's two ways to solve a problem that can be solved with depth-first search. You could do it recursively or iteratively. And when you do it iteratively, you use a stack. Some key terms, and we'll go over these when I show you the first, I have a few diagrams. You have a root, you have a node, you have parent, children, and then binary and n-ary are types of trees. Okay, so we are now going to look at an example of n-ary trees. One moment. Here we go. Of trees, and I'm going to kind of just do a very quick review of some of the key terms. So can you guys see, I'm circling around the 5 right now? Or Elaine, maybe you're not on mute.
Yes, it's visible.
Awesome, thank you. And so this is an example of a binary tree. Bi comes from the word, bi comes from the from two. I forget which language. If you know it, put it in the chat. So right here we see that the node is splitting into 2. So anytime you see that one node can max split into 2 other nodes, that's a binary tree. An n-ary tree is because you literally don't know how many children it could have. Like A right here has 3 children, but C doesn't have any children. But then B has 2, and then D has 3 again. So an n-ary is for anything more than 2. Now, the 5 right here, the 1 right here, the 4 here, and the 1 here, these are all called root nodes. These are the nodes that you start at. Something that is below the root node and linked to it is its child node. In a binary tree, you have something that is called a left node, which is the node to the left of the root, and the right node, which is to the right. In an n-ary tree, you just have lots of children. You can say things like leftmost and rightmost, but you do not have the concept of left and right for an n-ary tree. To make sure I'm going through all of the terms, parent node, children, cool. I think those are all the main concepts, and as we go through the slides, I'll spend some more time on the n-ary and the binary pictures. Okay, so you often hear depth first search and phrases like top down and bottom up. Top down and bottom up are phrases that talk about different ways to use recursion to solve a problem. In depth first search, top down is done with a pre-order depth first search, and I'll show you what that is in a moment. Bottom up is solved with a post order. When you see us do pre-order, you will see that we're literally going from the top all the way to the bottom of the tree. When you see us do bottom up, you'll see that we're actually going from the bottom of the tree all the way to the top. So it's really awesome and easy to memorize because like it literally looks like that. Okay, so now we're going to look at the previous diagram and learn about bottom up and top down. So when we are thinking about depth, depth means going to the root node and then continuing all the way down until you get to the bottom, and then going back up to the root node and continuing down until you're ending, going up to the root node and continuing down until you end. This is different than breadth first search, which looks at every level. And so you'll often hear breadth and level used interchangeably. So an example of level would be here. So here you will see I have 2 on my first level. On my second level, I have 9 and 20. On my third level, I have 15 and 7. And so you do things level at a time. So if I were to do this one, I were to look at this tree, and again, it's the same tree in all 3 of these n-ary trees. If I were to do something in level, I would literally just go A, B, C, D, E, F, G, H, I. And you can see that in the way it's represented below in the array. With depth first search, you don't do that. Depending on which type of search you're doing, you put things in a specific order. So pre-order starts by going to the top and then to the leftmost node. And then if that node has children, it goes to that one's leftmost node. And that's how you go down. So if you are doing depth first search, you will go as far down as you can. However, depending on where you, depending on what kind of depth first search you're using, you may add the node at a different point. For example, pre-order. In pre-order, I start at the root node. I immediately add it. I go to its leftmost child, B. I immediately add it. I go to its leftmost child, E. I immediately add it. I see it has another child, so then I go to that child, F, and then I add it to the order. Okay, so I'm finished here. Let me go back up to A. A's next child, next leftmost child is C. I add that because it doesn't have any children. Then I go back up to A. It's already been added again, so I do not add it again, but I need to go back up to access D. And so I add D because now I am there. And then I go to D's leftmost child, G, and I add it. What's the next leftmost? H. What's the next leftmost? I. I hope this is easy to see how you're kind of going down, down, down at all times. So you go all the way down and then back up, all the way down and then back up, all the way down and then back up. Now, post order. So this one is called pre-order because the node always goes first. Post order, think of the node as going basically last. So let's look at post order. We are starting at the top with A, but look it, we didn't add it yet. We go to A's leftmost child, which is B, but look it has not been added yet. We go to B's leftmost child, which is E. oh, hey, it has no children. I'm going to add it. Then I go to B's next leftmost child, which here happens to be on the right. It has no children, so I add it. Then I go back up to B. I've already added its children. It doesn't have any other children. And so then I add B. Now I'm going back up to A, but A still has other children for me to look at. So I'm not adding A until I have added all A's children and the children of A's children. And that's how you get post order. So for post order, think of go all the way down and then back up. And then if there are more children, continue going down until you have all the children of that child, and then go back up until you have all the children of the children of the children, and only then do you add the root node. So we're talking about with recursion, and in recursion, you have top down and bottom up. And you can very, very easily see this with pre-order and post-order. In pre-order, I'm literally going from the top to the bottom and adding my nodes. From post-order, I'm literally going from the bottom to the top to add my order. And so these are good for solving different kinds of problems. For today's exercise, we're going to focus on pre-order, but if you would like to practice post-order, the cheat sheet I have in the slides links you to all the practice problems for post-order with some solutions. Okay, so today you guys have a choice. I have two questions. One's easy and one is medium. I can either solve both of them recursively and then iteratively, or I can solve each problem recursively and then iteratively, English, huh? And then I can move on to the next problem. Would you guys like to see one problem at a time with both solutions? Or would you prefer one way and then the other way? First way, okay. Thank you, Yash, for putting in the chat. Second way from another person. +1, 2, I'm not sure which one. I'm seeing first. Seeing first so far. Cool, alrighty, I see a lot of first, so we're going to solve both recursively and then go to iteratively. Okay, so let me see if I have them. Cool, I have them currently in that order, so we'll do that. Okay, so the first one we're going to do is an easy problem. Just to be perfectly honest, you will never get this in a, well, I don't think you will ever get this exact question in a coding interview, but you need to know how to do this in order to be able to do the other kinds of questions that will come later. So here's the problem. So I'm going to open that up. Oh, actually, I had it open, so go there. Let's reset this. Confirm that. Alrighty, the solution here, you can see, so while I'm working on it, you can look at kind of where I'm going to go to. I might change a few things depending on input as we work through it. And then here is the diagram. Now we're going to look at the diagram as I explain to you what we're doing. Okay, so this is our first question. Please take a moment to read the question. Something I forgot to mention earlier is what is the word leaf. There is a note here. A leaf is a node with no children. So the solution I'm about to show you is going to work for both minimum and maximum depth of a binary tree if you just change one little thing. So to first help you understand how to think about the problem, we're going to go to the drawing. So this is the drawing I showed earlier. It has what we're looking at. If I were to go through this by depth, I would go 2, 9, and then I'd go back up to 2, and then I'd go to 20, 15, 7. Now, for purposes of this exercise, we don't really care what the numbers themselves are. Oh, I see a question. Is DFS the desired approach for this problem? You can do this multiple ways. Because DFS was what most people wanted to focus on for this question, I am doing it in a DFS way. And I'm specifically, I think, doing a pre-order way, but I will confirm that once we start going through it. So the way we would go through this would be to kind of note where we're at. Okay, so let's have an array. So I know I have one level at level 2, and then I go to level 9, and I'm like, okay, cool, that's level 2. Then I go back up. And, oh, sorry, I forgot to note, we know that a thing is a depth, is like the final depth because it is a leaf. So let's, let me put that on here. Leaf is a childless node. And so in this instance, we have 3 leaves. The leaves, I don't know if you can say leaves plural, but the leaves are 9, 15, and 7. Okay, so we go to 9. 9 is a leaf and it is at level 2. Cool. Now we're back up at level 1. 2 goes to 20. 20 is not a leaf. So we are going to kind of leave it out. However, 15 and 7 both are, and they are on level 3. Because they are both leaves, we're going to put the level twice. So I messed up in the beginning and I put 1 when I shouldn't have. So let's do that again so that it can be clear. We are at 2. It is at level 1. However, oh, someone has a great idea, son and grandson. Please explain again. Okay, so we are at the top, level 2. Is level 2 a leaf? No, because it has children. So we always go to the left first, right? So the leftmost node is a value 9. Now, does the node 9 have any children? It does not, so it is a leaf. Thus, I am going to make sure I recognize that I am at level 2, and that is the maximum depth for my left node, okay? Now I am going to the right side. I would like to say, okay, somebody is noting there are multiple ways to do different orders. Agreed. All right, now we're going to 20. 20 is not a leaf because it has children. Now we're on 15. 15 is a leaf because it does not have children. Okay, and so what level is 15 on? 3. Cool, we've added it up here. Now we're going to the other node, a child node of 20. 7 also is a leaf because it is childless. It does not matter that we are adding both of them because they're the same level, and the way we're going to solve it is going to enable us to get what we need either way. So if you were trying to solve for the minimum depth, you would take this and you would kind of put it in a function to find the min of the array, and then you would get 2. If you were trying to find the max of all the depths, you would have this, a function like this, and it would return 3. So very quickly, I want to make sure people are okay with this. I'm showing that regardless of min or max, we are trying to get all the possible depths listed. So we only want the depth when it is a leaf. And so we have added 9's depth, which is level 2, and 15 and 7's levels, which are 3. And depending on what you do with that array of values, you can get either the minimum height or the maximum height of the tree. Now we are going to go to solve it recursively. Let me move it over. Let me see. All right. So, oh wait, hold on, I have it wrong. What open on my side? Okay. So something you always need to check is if it's a node. Actually, we're going to backtrack. Generally, when I am doing a problem, I like to separate two sections. I like to separate into initial and then my BFS function. Oh, sorry, this is DFS. Oops, DFS function. I also do the same thing for BFS, so this is just how I organize it. And organization also makes it a lot easier. Cool. So I know that eventually I'm going to need to solve for minimum depth. Now, you are going to have situations where like root does not exist. So just to start, always check for root. Now, if root does not exist, then there are 0 levels. So if not root, we're going to return 0 because there are literally no levels. Next thing we are going to do is we are going to understand that we need probably an array of all the depth of leaves. So we'll call this, Python uses list instead of array. That's the name for it. So we're going to call it list of leaves. And then we're going to use our DFS thing here. And we have not yet defined what we are doing in it, but note that we are going to use it to get the list. Now, when we have a list, we want to make sure it's sorted. So there's 2 ways to do this. We can either sort our list and get 0 index. This is for min. Again, we're looking at min. Or, so that's option 1. Or we can just use the min function on the array. And so we have options of doing that. And then in the end, we are going to return the minimum depth. So for now, let's think about using minimum. So we know our minimum depth is going to be the minimum of our list of leaves. So just so you kind of see how it's working out, I know that I'm going to have to check for root always. And so make a note of this. When you are starting out, they might screw you, just always check for it. If there are multiple tests, they will test this one. So just always start out checking for root and return what should be returned. Sometimes you're not going to return 0, so make sure you read your question carefully. And then you know that I'm going to use my depth for search somehow, and I'm going to get a list of all my leaves, right? I'm going to figure out where the hell the leaf levels are. And then I know from this list, I need to get the minimum one. So this is setting us up for the basic structure to get the final answer. Now here comes the hard part. We now need to look at our question and figure out how we're going to use DFS. Let me see, minimum depth of a binary tree. Okay, so let's look at our requirements. How do we tell we are at the end? How do we tell if we are at a leaf? How do we tell? There is no, and we can see here that we have a definition of tree node above. Oh, awesome, thank you, Nidhi. Said in the chat, when there is no child. So because we know that there's a potentiality for a left and a right, we are going to check has children, okay? So has children. Does this leaf have children? And how do we figure out if it has a child? We are going to look for a left child, which we will find. I like to call it node. So we're going to have a node that will be passing through. And so we'll go to line 25 and we'll pass in the root to start it off. Oh yeah, feel free to unmute. Thank you, Elaine. All right, so we have a node, and how do we find if there's a left child? We check if node.left exists. How do we find out if there is a right child? We check if node.right exists. Okay, so how can we tell if we have children? We're going to be able to tell if we have children if there is a node.right or a node.left. So now we're able to figure out, do we have children? Now, this is going to be used later because to add a level for a leaf, we need to check the children. So in order to check if that is the node that we are passing is a leaf, we need to be able to check if not children, do something. So something else we are going to pass in, I've decided, is an empty array. So look on line 31, and that is an empty array. Okay, so we have a list of leaves. That is an empty array when we're passing it through the first time. So if we get there and we see that there are no children, we're like, yes, we found a node. So we are going to need to input something. We are going to need to append to the list of leaves a level. But look, right now, we do not have any way of checking for level. So let's come back to level. So at some point in here, we are going to get the level. Let me open my screen a little bigger to make sure you guys can see. Let me see. Let me check. All right. Oh, yeah, you can see most of the bottom. Okay, now you should be able to see everything on the screen to minimum depth. Awesome. All right, so we're going to come back to level. So if there's at all points, we want to be able to return the list of leaves. Even if we don't add to it. Okay, so now we're kind of figuring out, all right, we know how to tell if there's a child. We know that if there are not children, we found a leaf and we need to like append the level. But how do we get the level? How do we get there? And that actually is not that hard. It's actually easy once you get in the swing of things. I know that when I'm at the root, if there is a root, that I am on level 1. So we see here that if I have a root node, I am on level 1. So I know that I can pass 1 into my function. So let me now say level. And so that you know, level is always going to be an integer, and leaves will always be a list of ints. And then I think because I'm typing import list, just so I don't get any like error, Will Robinson error. All right, so let's see. So now that I know, oh, I can pass the level, cool. So for example, if we were at, let's see what we have here. We have 3 here, okay? Pretend 3 was the only girl in the world and it had no children below it. So if we got to if not children, we would append 1 because that's what we had passed through. Now, what happens when children exist? We need to go say hi to them because obviously we're not at a leaf yet. So we're going to check each child separately because they may have a left, but maybe they don't have a right. So if node.left, do something. If node.right, do something. Now here is the beauty. Oh, I love it so much. Here is the beauty of recursion. I get to use the function that I just wrote. I get to basically call it on itself and it does all the things I want it to. It's very fun. So if I'm going to use recursion, I'm going to call DFS. Now I need a node. So if I am looking at node.left, I'm probably going to be using that as my node. Now, level. What would the level of this node be? It would probably be the level that came into it plus 1. Let's check that. So for 3, it has children, so we need to go down, and we have 9. So if no dot left here was 9, and we know the previous level was 1, if we on line 25 have 1 plus 1, we get level 2, which works out. Let's go back there. Cool, cool. All right, so far I know I see that on line 11, I need to have a node, I need to have a level, and I need to have a list of leaves. What am I missing? The list of leaves. So let's add that. Cool, all right. So I've taken care of my left child if it exists. Now, what if I have a right child? Ladies and gentlemen on tonight, we do literally the same thing, but we replace no dot left with no dot right. So let's walk through this. So if I have a no dot left, I'm recursively going to go through and check, is this a leaf? And if it's a leaf, it's going to add it, or it's going to append whatever level the leaf is at to my list of leaves. So that in the end, when I return my list of leaves on line 41, I am going to have an array. Now this one will look like something like this. So again, right now we're doing the minimum. So the minimum here is going to get us 2. But if we were doing the max one, which is another problem here, you could very easily just turn min here to a max and to get that from the array. So let's see what happens. Ooh, I have syntax error or a no dot left. Oh man. Alrighty, I gave it one too many arguments. So let's see. What line is this? Line 41. Let's see. Root 1. Okay, I take 3 there. Okay, it takes 3 positional arguments before or given. So I have 1, 2, 3 there. 1, 2. I have the root I'm passing. I have 1. Does anybody see what I'm doing on 41? Let's see. Oh wait, hold on. That was not what I was trying to do. Get it back, get it back. Alrighty. Self is missing in the DFS. Do I have to pass it again? Ah, yes, so smart. Thank you. I forgot to put it up here. Thank you. Thank you, Maria. All right, so now we see that the answer works. But we want to make sure that it solves for all possible cases. So let's submit it and let's see what it does. Cool. So it's not super fast, and recursion generally is not the fastest because of the way recursion works. But it gets the job done. So this is how to recursively solve this problem. Questions?
Can you please give the first left node as null and check how does it work?
So for, would you like me to go through, I guess, walk through it going through 3 and 9? Would that be helpful?
Yeah, instead of, yeah.
Mm-hmm. Okay, so let's go through this with everything. All right, so I have a root node. Okay, I have a root. My root here, look on line 33. My root is value 3. And then so I'm going to pass the following on line, let's see. So this is going to be what list of these is going to return. We're just going to ignore that. So what I am passing here on line 41 is going to be self.dfs, and the root will have a value of 3, okay? It's going to have the whole thing attached, but just so you can see the value, it'll be that. And then it will be this. Let me open it a little wider so you can see that. Okay, so now we are going into the DFS. So let's go. We are in the DFS and we know our first node, level, and list of leaves. So first iteration, I have 3 as my node, I have 1 as my level, and I have an empty array. Now, I need to check, do I have children? Now for this one, on line 19, you could write it this way. You could also very easily write it this way. Because it's an or, it doesn't matter as long as one of them exists. So children, node right or node left? Yes, there is a node right and a node left. So yes, it is true. So let's print. Actually, maybe that would be helpful. Let's print children so that you can see it. Okay, so children here is not going to be a Boolean value. It's going to be whether or not there are actual children. And so the actual value are tree nodes. Do you see that? And when there are none, it says none. Is that helpful for visualizing it?
Yeah.
Okay, so now we're going to either have, so if we have right or left, it doesn't matter. So if node right comes back as we have right now we're going to return node.right because there are children, we don't care, we just want to check are there children at all. So node.right will come back and all of the tree nodes associated with that. Okay, so now we're on 3, right? So 3 has node.left. Node.left is 9. It also has node.right. Node.right is 20. Now let's go down to line 30. We have if not children. Now it has children. So we're going to ignore that for now, and we're going to do the 2 above. So we are at node.left. So let's do our next iteration. I'm going to show an iteration by this little arrow line. Okay? So when you see the arrow line, you know we're looping through. All right, my next one, node.left is a value of 9. My level is now 2 because I did 1 plus 1, and I still have an empty array because I haven't found a leaf yet. So I am going to look at 9. Does 9 have child.right? No, that's none. Is there node.left? Nope, that's also none. So that's what we'll get for child or children. Because it doesn't have a node.left or a node.right, we're not going to do either of those. That's lines 24 through 27. We are going to get to if not children. So here it's none, which is going to mean not children, and we're going to append our first level. So when we started this iteration, we saw that our level on line 13 is 2. So I am now going to have a beautiful, beautiful array of 2. Okay? So we're going to now go back up. So I have done my list of leaves, node.left 9. Now I am getting to node.right, and this is the node.right of 3. So I am here and I'm like, okay, cool. Let's go through this. Let's iterate. And because of the way I wrote it, left will happen first. Technically, you could write right first, but I tended to notice that performance-wise, it's a little slower, but for purposes of this specific one, you could put it first if you really wanted.
Can I ask you, I've got a question for you.
Yes.
The return line on 33.
Yes.
So on line 25,
Mm-hmm.
where does it return to?
Line 25.
Because you're gonna call, you're calling it.
Mm-hmm.
I don't know where. So like,
Mm-hmm.
you've got your list of leaves. You've now appended 2 to it.
Mm-hmm.
Where does that get returned to?
List of leaves already exists, and so it's getting returned in there. So let's see if I can print it. So let's see it, and this will
Since it
help.
is dispersion, it is
What? No, but
Back
you're
up in the
returning lists of leaves to where? Like, where's it gonna be? Is it? Is there a reason you're returning the list of leaves? Is really my question.
It's returned at the end because list of leaves exists in the outside scope. It's basically just pushing it through there. So let's see here, we have this one. So when you see the first 2, do you see the first 2 and the standard out?
Mm-hmm.
That is coming from when I'm in node.left and I'm doing 9. And then you're going to see 2, 3. That's when I am in node.right and I've gone to 15. And then when I do 7, you are going to see the last iteration of 2, 3, and 3. Does that make sense?
I guess what I'm saying is it seems like the DFS function itself, the only reason you have the return line on 34 is because somewhere in your min-depth function, you need it returned because it's assigned to some variable, right?
Yes, correct.
Otherwise alone, you wouldn't need that line, sounds like.
Usually you will need something like this when doing like DFS problems because you'll have to check it in the original. So in like min-depth, you'll have to check it. So usually you will have an array of some sort that has to keep getting passed through when you are doing it recursively. Did that answer the question on going to the left? I could answer and continue to go through to the right, but I want to make sure I am cognizant of time if you would like to see the medium problem and then perhaps the iterative solutions to both. Okay, are we okay with moving on to the next problem?
Yes.
Cool. All right, so I am going to reset this. Actually, I'm going to post it really quickly in the SF algos so that you have access to my real-time ones, not just, let's see, so SF algos, I'm going to post that real quick, just so it's there. Uh-oh, what happened, Slack? Slack, go faster. One moment. Let's see, create a code or text snippets. Cool, I'll put more information on that later, but it's in SF algos, so you guys have that one for now. Exactly the way I wrote it here, because the one that's in the code base where I showed you is a little bit different from this and doesn't have all the notes. So this one is now in SF algos. Remember, SF algos channel link. I think it was, who was it that you were supposed to first, I forget which of the volunteers, send them your email. Oh, yay, Monica. Send Monica your email, and then once you get invited to the Slack, it's I'm posting this in SF algos, literally like that, and you can join it and see all the information there and stuff from previous sessions. All right, so we are now going to this one. Okay, so this is one I've actually seen in an interview. I don't remember which company it was for, but I've seen this one. So it's a good one to practice with and know. We have the Leetcode problem, we have the solution, and again, the solution has both the recursive and the iterative, and we have a drawing. So let's go to the drawing after I let you read the question. So this is the question. Sum of nodes with an even valued grandparent. Remember, trees are all about parents and children and lefts and rights. This is an n-ary tree, so this is just gonna have, oh wait, no, this is a binary tree, so this will have a left and a right. So we're going to look for nodes that have an even value. And basically, if they have grandchildren, we're going to add the sum, add to a sum of some sort. We're not adding the even value. We are actually adding the grandchild's value. So let's look at what that is. So I have handy dandy drawing in front of you. All right, we are going to together look at the even nodes. So can I have somebody give me the first even node? Shout it out.
6.
Yes, yes, I have participation. All right, cool. And let's do the next even node.
8.
Awesome. And are there any other even nodes?
2
Sweet.
and 4.
Awesome.
Sorry, I
All right.
was just fast.
No, it was great. Thank you for saying them out loud. All right, so we have identified all of our even nodes, right? Cool, that's the first step. Now we need to see, do these have grandchildren? So let's start with node, the node with value 4. Does the value of node 4 have children? This one down here at the bottom. Does this one have any children?
No.
No children.
No, so it's not going to be able to have any grandchildren, huh?
Yep.
No children, no grandchildren. All right, let's look at 2. Does 2 have children?
Yes.
Awesome. However, does it have grandchildren?
No.
Cool, so took care of that one. All right, let's look at 8. Does 8 have children?
Yeah. Yes.
Cool, all right, so let's move this over. Move this over. Awesome. Alrighty, now it looks like 1 does not have any children, right?
No.
No, okay. But 3 does. So does 8 have a grandchild?
Yes.
Hallelujah, we found the first one. Alrighty, so I am going to add that to the grandchildren values. Right now, we have a 5 added. Do you guys see grandchildren values at the top?
Yeah.
Cool. Alrighty, next one, even node of 6. Does 6 have children?
Yes.
Sweet, okay. So it has 2 children. What are those numbers?
7 and 8.
Awesome. Okay, let's start with 7. Okay, does 7 have children?
Yes.
Cool, all right. That means the node with the value 6 has, what does node value 6 have?
Grandchildren.
Yes, alrighty. So what's the first grandchild?
2.
Awesome, let's add that value. So it's added to the grandparent. All right, what's the next grandchild?
7.
Awesome, let's add that value. Alrighty, let's go back up because we said 6 had 2 children, right? We've dealt with the leftmost child, let's deal with the rightmost child. Okay, so it has a child of 8. Does 8 have children?
Yep.
Awesome, that means that 6 also has grandchildren on its right side. What is the first grandchild?
1.
Awesome. And we're going to add that value to the top. Let's see. And does it have another grandchild?
Yeah, 3.
Awesome. Do that one. Ooh, let's see, moving that. Cool. Alrighty, 3. Alrighty. So let's see. We have all of these together. Oh, hold on, my spacer is not working. All right, so we have all of these together. And then we'll probably do something like sum, right? We'll just sum the array. And when we sum all these together, I believe we get 18. Can someone check my math?
Yep, I think so.
Awesome, okay. So you have a very visual picture of all of the grandchildren here. Do you see how some can be grandchildren and parents?
Mm-hmm.
Okay, do we see all visually, do we understand where the grandchildren are? Kind of, yes?
Yes.
No is also an okay answer. I could explain more. Okay, so let's see, did we get the right answer? Cool, we got 18, and that's what it is. So now let's see, how are we going to solve this? So you all saw in the last thing that I kind of like to separate things out. I have my initial, and again, I only do this when I'm solving it recursively. I have my initial, which is sum, even, grandparents, and then I have my my DFS thing. Do all the things here. All right. Now, we always kind of have to check for something usually. And that is if the node does not exist. So usually we'll put in check that there is, hold on, does it say there's always going to be something actually? Oh, hey guys, always check your constraints. Do you see constraints here? We will always have roots. Do you see that? The number of nodes in the tree is between 1 and we don't care about the other number. Do we see that on constraints?
Yeah.
Cool, awesome. So we don't have to check that node exists or the root exists. Awesome. Now let's think, how am I going to solve this? So I'm probably going to need to get like, now you can do this with an array or you can just keep adding for some. I like to do it with an array. It just keeps me in a specific pattern and it helps me to solve things more easily since I have my pattern. So again, you're going to be able to do this either with just adding to a sum. The way I am choosing it though is to use this as an array. So I'm going to have a grandchildren sum array. And in the end, I'm going to, I am going to get a total sum, which is basically going to be the sum of the grandchildren sum array. Cool. So I know that in the end, I am going to return a total sum. Awesome. Ooh, sorry, got something. All right, now I need to figure out what I am going to do. I know that I'm going to have to call this other thing, but I don't know what I'm going to do with it yet. So let's think about it. Let's see what I'm going to do. And we'll come back to this here. Alrighty, so what am I doing? What am I checking? There has to be a node, right? Because if there isn't a node, I'm not checking anything. So I need to check for node. That's the first thing I need to do. Check node. Question?
Don't forget to pass self into the DFS.
Oh, yes, because I forgot that last time. Thank you. Thank you, appreciate that. Alrighty, so I need to check node. So how do I check node? If node, super easy. Now, what do I need to do? I need to understand is my node even? Now, how would you tell if your node is even? We can use a very easy symbol. We could do node.value modulus divided by 2 equals 0. All right, so is even. So this is either going to return a Boolean of true or false. Just so you can see that there. Okay, so I know that I need to be able to tell if something is even. And then if it is even, then check grandchildren thing. So if is even, I'm going to do many things. And then in the end, I'm probably going to have to return something. Now, what do I have to return? Grandchildren sum probably. So let's see, am I passing grandchildren sum? I am currently not. So let's go back to line 23. I know that to get the whole thing started, I need to pass root. And then I know I want to pass grandchildren sum. And then I know that because it's down here, I need to make sure I add it up here, or else I will get yelled at by the thing below. Okay, so let me check to make sure I'm doing all of it.
Can we just call it grandchildren since we're not taking the sum?
Which line are we looking at?
Just the grandchildren sum list that we're passing around.
Oh, return it.
We're not actually taking a sum.
Oh, you want to change the name? Yeah, let's do that. Let's do that.
Thanks.
And so we can rename this one. Children, that could be grandchildren sum, and then this is just going to be grandchildren.
You're missing a D on line 23.
23. Oh, thank you. Yeah, that would have complained, right? Okay, so now we have an array of grandchildren. Let me make sure. And then we're going to return grandchildren. Maybe I don't even actually have to, because no, remember on the other one I returned here, grandchildren, and then I just passed an empty array. this also seems to work as, so apparently you can do both ways. So I'm going to show you 2 ways because apparently this worked on the other one, and we'll test that they both work. You can do this one. And then to make it consistent with the other one, option 1. Option 2. And you can pass it in like that, I believe. Alrighty. Okay, so let's see where I'm at. Passing
The
in
line
there.
32, return grandchildren's son. The line 32. Yep.
Thank you. Gotta make sure we update everywhere. All right, let us go to the DFS now. Alrighty, so I know that I need to check the node. I know that I need to check is even, but like, how do I get everything I need? I need to, how do I tell if something has a grandchild? How do I tell if there are grandchildren? Let's see. Well, if node.left, there is a parent. If node.right, there is a parent.
You mean
Now,
a child? You mean,
oh, child. Yes, God bless you. Thank you. Child. All right. And now if node.left, there is a grandchild. If node.left.right, there is a grandchild. Cool. Okay, so I'm thinking about, all right, that's how I can tell if this one node has a grandchild. Cool. And then how about the rest of it? So if I'm node.right and I want to check for grandchildren, I'll probably check node.right.left. There is a grandchild. And then if node.right, there is a grandchild. Apparently I'm having trouble with my D's right now. Okay, cool. So this is showing me that I can get grandchildren. Okay, so let's see. So how was I checking? If, oh, whoops, sorry, I put this in the wrong area. Let me move this down a little bit. Sorry if that was confusing to you all. Should have gone right here. So if even check grandchildren thing, how do I check if there are grandchildren? Okay, all right, so let's put this into code right now. How do I check this? If node.left. Cool, how do I do this one? If node.left.left. Super awesome. How do I do the next one? If node.left.right. That's awesome, right? Because it basically looks like what we wrote, node.right. And then let's go back to if node.right.left. Now, guys, if I write any of this wrong here, it's going to screw everything up. So please look at it. You have to write them in the and make sure that they all are where they need to be. Because if I had like 2 node.right.lefts, it would not work out. Okay, so I now have all my checks. I can check if there are grandchildren. Cool, but I need to figure out if I have grandchildren, like I need to add a sum of some sort. So let's see, I'm going to have a grandchildren sum here. And this is different from the one below. And I'm going to set it at 0, okay? So if I have a node.left.left, that means I definitely have a grandchild. So if I have a grandchild, I am going to add that value. So let's see, how would I add the value? Very easily, like that. And then to make sure I am doing everything and not having errors, I'm just copy and pasting it. I would have that. So
I got okay. So
yes.
in your sum even grandparent function on line 44, you're taking a sum over what I thought was a list of just the grandchildren nodes.
Because at the end, I'm going to append it. We can go in and probably make this cleaner at the end. And that is something that we can do.
So how come you're doing a sum on line 16?
On line 16, because
Or like
I'm
on 21, you're adding a value rather than appending it to some array, some list.
So I could fix it and make it more performance. For now, I'm gonna continue with this one. Do you see where it is on line 31?
Yeah, but I thought you were just gonna add the values from any grandchild into that array rather than calculating some sort of sum in here.
I realize in retrospect that I have to account for 0. So let me do it like that. Let me now. So let me account for it down here, because if grandchildren, this length of grandchildren, let me account for it here, and then I can change there. Length of grandchildren equals 0, returns 0, else grandchildren sum, grandchildren. All right, cool. We've accounted for the difference, and I can now do that. So let us see, where was I at? So I was just going to add it. I was just going to append it here. So let's go to grandchildren. Grandchildren dot append. There we go. Cool. Alrighty, and then we can do it for the next one, because we're basically, if it exists, cool, we're going to add it. Okay, let's make sure we're adding the right thing. When I first did this problem, I copy and pasted the wrong things, and it did not work out. Alrighty, let's do this one next. Okay, so now we're doing a really great job if checking if the current node has grandchildren, but we're missing a way to check if nodes below it have grandchildren. And so right now, what we would get would not be 18. Right now, what we would get would be 18 minus 5, which is 13. So on line 12, what do I need to do to make sure I check the rest of my nodes? What do I need to call?
Recursion?
Yes. So we're going to call self.dfs and self.dfs. Awesome. Okay. So right here, we're checking if node. So that means that we don't have to check on 12 if node.left or node.right exists, because when we go through DFS, it'll automatically check that for us first thing. And we'll just return the grandchildren.
You got 2 lefts there on line.
Oh, thank you. Oh yeah, that would not have worked out, right? And then I also want to make sure I'm passing it the grandchildren again. And so this will enable us to go through every node and verify for every node, does that node have grandchildren? So let me see, let's run code and let's see how this works. Grandchildren is not defined. Where did I put it? Plain. Oh, there's the D again. Let's try it again. Okay, so do you see how this works out to 18? Let's submit it and see if it works for everything, and it does. So now is the time to, oh, actually I want to show you the, let me see, does this one work? I want to show you that both option 1 and option 2 works. So let's see, hold on, I want to show you both options. So let me see, return, what is this, return, grandchildren. Oh wait, no, I would have to change things in the DFS for that to work. That's when I originally had the 0. So we're going to ignore that, and we're just going to stick with this option just to make it a little easier to understand. So let me see, make sure you can view the entire thing. All right, question time.
Yeah, can you scroll down a little bit or zoom out or something?
Are you able to see it now?
Yeah, got it. Thanks.
Awesome.
Oh, I see you can't take a sum of an empty array. Does that throw an error in Python?
The problem is not, yes, that will throw an error, I believe. And then we also need to make sure, because it's stipulated, I forgot to show this, if there are no nodes with an even valued grandparent, we need to make sure we return 0.
Okay.
So that's basically why that is line. I'll put that so that it's more obvious.
So can we expect such kind of questions during interviews?
Sorry, say it again.
Can we expect such kind of question during interviews rather than the easy ones?
Yes, I would. I would say that medium and hards. So you need to start with the easy though, just so you can get the pattern down. In the cheat sheet I made, I have a lot of like how to go through them, and I've written some comments in there. So these are very, very hard. It takes a long time to, one, figure out how to even iterate through them, and two, to recognize some problems that use them. The hard one I was going to do today has something that I wanted to show for a pattern. If Elaine wants, I could do one that's just the hard problems and show you some of the ways that they're used. But I think this one is a really good basic one that, yes, is asked at a question at a big company, but is not as unattainable as some of the hard ones. So this is a really good one to start with. And then they have some, I think here on the bottom, what are they related? Is it related topics or related questions? The questions, where are they? Do not remember. I guess this one doesn't show you related questions, but if you go to the cheat sheet, I have a bunch of different ones if you want to practice this at all different levels. Oh, how long would you be allowed to work on such question? This question, if you are not senior, 45 minutes. If you are senior, half of that time. And then hold on, Julie, let me see what you wrote. Let me just check for grandchildren by. Oh, okay. So why did I do if node dot left, and then I think it returned an error, Julie, when I originally tried to do it without the node dot left. I think I got errors because I needed to first check for node dot left. It was like no node dot left, therefore you can't even check the dot left to like a none. Oh, awesome. Yes, Elaine just wrote it. Cool.
Hi, Krys.
Hi.
So it looks like for this problem, it doesn't seem like it matters whether you call the 2 lines of recursion before versus after you actually process a node. For like if lines 12 and 13 had been somewhere below, somewhere before the return, I'm thinking it would probably work the same. But for other problems, it does matter. So
Yes,
the question is, how do you decide between doing post order and pre-order, which I guess is what that really means?
Yes. Okay, so for here, let me see. So I'm putting it at the end. I'm checking the node from the beginning, and then I'm going through. It usually depends what you're checking and what you're looking for. So let me look at my, I think the iterative solution might show a little, hold on, let me look at my iterative. I think that was helpful for explaining why this is pre. I think this one is good for pre because you just have to check the node. You can't do anything else without the node. And so for, let me see, this work at the bottom. If node.
Well, what I mean is, you know, it doesn't appear to matter if lines 12 and 13 were moved down to somewhere between 34 and 35. I think it would still work. I think the list of grandchildren would come out in a different order, but the sum would be the same because you just care about the sum. So, but there are other problems where it really does matter whether it might matter whether or not you process the node, which is all that you've got between
Mhm.
16 and 34.
Mhm.
It might matter whether or not you do the processing before calling the recursion or after. I don't know.
Let's go to my cheat sheet. And then let me check a few examples there. So let's see. Those are level order. Let's look at, so here's pre-order. Path sum is definitely, I think, one you have to do. Let's look at post real quick. That's in order, post. Oh shit, this one was post, not pre. I thought I did it both ways, actually. Oh, this one was post. Let me check, left, right, then node. Okay, that would make sense. Okay. Huh, hold on. Sorry, I thought I was just pulling pre from you. That, yeah, then that makes, okay. So then that will help me explain it. Sometimes I get things wrong when I'm ordering them or saying them out loud. So let me go back to some of nodes. So this is pre, this is post. So that is not confusing. We're gonna write it here. Post. Post order, okay. And then let me see, how do I know that I have to do it this way? So for post order, let's look at the tree. Oh, here's the trees for post order. So for post order, I'm always going to do this way. Sorry, I'm trying to think of how to explain it. I know to do that.
I mean, isn't it pre-order, but by doing it recursively, it ends up being, I mean, the
No, I
opposite.
don't know how to explain it. Elaine, do you know how? I'm having trouble explaining it.
I mean, if you call the recursion before you process the node, then I think it's post order.
I believe so, because of, yeah, before you process the node.
All of the results are going to percolate upward from the bottom of the trio.
But it should also work what you're saying for the other way. So let me see if just changing that still works.
Maybe if you printed what comes out on line 39.
Yeah. Let's run here.
If you
okay, so yeah, this is showing it works both ways. Let's see if it works. Let's see if it also, we also need, okay, that works both ways. So for the purpose of this, we don't care about the order of the sum.
Right.
So I was doing this at post, but because you don't care about the order, yeah, it doesn't matter. This could be pre or post. Post order to before node processing, pre-order to after node processing. Okay, so just so you guys have that.
Yeah, I guess my question was really, is there an easy way to recognize, is there an easy way to recognize when you get a prompt, oh, this is definitely something I want to do bottom up versus top down? Like,
check this. I think this one
patterns we should be paying attention for.
There are patterns. I apparently did not write them down well enough for this. Let me look at the hard one that I was going to do, and let me see if that one's a more obvious one. Let me see. That one shouldn't care either. So you can see here on some of the solutions, there's this BFX. Does it talk about it? There are ones that count. I'm going to put a note to myself in the Slack to come back with, and I'll give you guys an article on it because I cannot explain it off the top of my head right now, and I should be able to. So I will put an article for that.
Hey, Krys.
Yeah.
So in this case, if it was not the sum, and say we had to print the ancestry level, right? I think then the ordering would have mattered.
Okay, say that again so everyone can hear.
Like if we had to print that, okay, print all the parents before you print the children.
Yes.
Right? In that case, the ordering would have mattered. You know, in that case, we would have to do pre-order because that's when the root would have gotten printed first and then it would have gone to the child. But since it's a sum that we care about here, I think that's why it's irrespective. Like you can do both. At least that's my understanding.
That sounds good. Thank you. And then I will also post something tomorrow. I set a reminder and I'll put it in the channel. I want to make sure, yeah, I should be able to explain this to you guys. Back to, okay. We are at, any other questions on this one? Okay, no other questions? All right, Elaine, I know we're getting close to time. I am willing to stay on and do the iterative solutions for both of these. And so let me know, is it best to continue and do the iterative now for both of these, or what would you like to see?
I am sure people would, and I would love to see the iterative. How about for one? And let's see. I guess I'll, do you have a preference? I'm trying to think about which would be better.
Let me see, let me look at my solutions for them. Let's see, let's do the grandparent one, since you're more likely to see that in an actual interview.
That's good, thank you so much.
The iterative solution, however, is in the in my cheat sheet. So for the one that I'm not doing, you can still see it there. Let's do that. All right, so iteratively is done differently. So you saw previously when I did this question, I had like def DFS. When you do it iteratively, you're basically, sorry, my dogs are being a little fun. Apologies if you can hear them in the background. When you do it iteratively, you basically keep it all in one. So that's the big difference. I'm not going to have a separate function for this one. All right, so let me see, how do you, okay. So big thing about iterative, when you are doing DFS, you use a stack. When you are doing BFS, you use a queue. I would highly recommend looking at these different data structures. They are crucial to being able to do problems, more advanced problems with trees and graphs. So make sure that you feel comfortable using stacks and queues. They will let you do some things recursively, but sometimes they will say, oh, okay, you did it recursively. Can you now do it iteratively? So please make sure that you don't just feel comfortable doing things recursively, that you also feel comfortable using, again, stacks for depth first search and queues for breadth first search. Alrighty, so a few things that we need to be able to figure out. So we need to be able to have a grandchildren sum. Right now, it's 0 because we don't know if we have any grandchildren. And in the end, we know we're going to return this grandchildren sum. Now, I know that I need a stack of some sort. So I'm going to put the stack there because you need it for DFS. Now, what is going to go in my stack? Now, something that you will find when you are doing these kind of problems is it's never just one thing. You oftentimes will have a tuple of things. So you'll often, whenever you're adding to the stack, so let's call it like first thing in stack, you'll often have more than one thing. So thing, the first, thing, the second, and we'll rename these. So know that you will have to do this. So let's see, stack. Usually what you add to stack is not singular. So tuples are common. All right, and then you know because you're using a stack, while the stack exists, you're going to do something. So while stack, do the thing. Okay, so again, the basics for if you are doing DFS iteratively, you will have a stack of some sort and you will add things to this stack. And then while the stack exists, you're going to do things to it. Now I have because of the way I'm doing this, I'm setting this to 0 because I need to make sure that if there's nothing and no grandchildren, I still return 0 here at the end on line 22. Okay, so what am I putting in the stack? What are some things that I need to know to be able to tell if there is a grandparent? I know I'm probably going to need access to a node. And here, the first node is going to be root. I know that I'm going to eventually probably need access to a parent and to a grandparent. Now, does root have a grandparent or a parent? It does not. So for now, you can set it as none. Yes.
Do we have this information, or can we only go downward?
We do not have this information. For root, we don't have this information. The way that I'm going through
even
it.
for a given node in a tree, wouldn't you be? Can you only check for children and grandchildren, or because here you're wanting to look upward in the tree? How would you keep that information?
As we go through it, I'm hoping it will become apparent. So let me, I guess, start to work through this, and give me about 5 minutes. And if not apparent, then we'll keep talking through it. So in order to have a stack, I need to put something in it, right? And so what is the first thing in my stack? We've realized that I'm probably going to need to have access to the node. I'm going to need to have access to a parent, and I'm going to need to have access to a grandparent. I need access to 3 levels if they, question?
Okay, so what you're really saying is you've put these variables in to keep track of yourself traversing through the tree. Okay, I get it. Yeah, thanks.
Okay, cool. And thank you for verbalizing it out loud. That was, I'm sure, very helpful for lots of people. So you can append to the stack, you can put it in the way I'm lazily doing it here. But this, putting first thing in the stack there, makes it work when we get to line 22. There is a stack, yay, we are going to do things, how amazing, okay? So literally when I code, I do write first thing in the stack because it helps me to remember I'm going to need something to kick off the stack. And I literally call the thing stack usually. And then while stack, do the thing. So this one is a nicer one. So when the first thing you do once you get into the stack is you pop from the stack. So we have a tuple here, right? We have 3 things from the stack. So what are we going to pop? We are going to pop a node, we are going to pop a parent, and we are going to pop a grandparent. And how do we do this? Stack.pop. It's beautiful. Now, what were some of the things? We need to check if the node is even, right? And then we need to check for children. So these are things that we know from the last time we did it, that we're going to have to do this. So how do we figure out if things are even? What do we want to check? Are we checking the node here, or are we checking the grandparents? What would tell us if we actually cared to add the node's value? So on line 26, what would help us? Which of the things that we are popping would help us know if we want to add the node's value? Is it the node itself? It's grandparent. Awesome. Okay, so as we can see on line 17, we don't know if there's going to be a grandparent, right? So the first thing we need to do is check if there is a grandparent. And if there is a grandparent, we need to now check that it is what?
Even. The value divisible by 2.
Divisible by 2, even, all those work. So if it meets our basic requirements, okay? So if there's a grandparent and it's divisible by 2, we are then going to add the node that we popped. We're going to add its value. So that makes it pretty easy because you do plus equals and then you do node.value. Now this is really, really great if we already iterated through everything. But as you can tell right now, we don't have any grandchildren. If we started with the original stack, it would look like this: 6, none, and then none. So we're like, crap, there's nothing, there's no grandparent because it's none. So I need to make sure I check for children for the node to continue adding to the stack to get all the values that I want. So we asked.
I have a note in line 26 when it modulating by 2. I think it's a grandparent dot value. Right?
Sorry, what are you asking?
Yes, I think.
It's saying in line 26.
Let me think of how I'm adding it to the stack. Let me.
Grandparent value modulo 2.
I think I'm adding the value. So the only one that I need is, oh, sorry, I forgot. Okay.
26, yeah.
So right here, this would be dot val.
Okay.
So right here, what I would be adding, and this you're going to see later. Thank you for pointing that out. This would be the dot val. The node would be everything.
Okay.
Everything. Yep. Not just dot val. Thank you for asking that question so I could clarify it. I'm sure that would have been very confusing to many people. So let's see. Okay, so how do we check for children, right? If node dot left, do thing. And then if node dot right, do thing. Now, we know that we want to append 3 things to the stack. So if node dot left, cool, we have a child. So let us now go, we have a stack. And we are going to append. And now our node dot left is the node we are starting out with. Now our node is the parent, and now our parent is the grandparent.
You might
need
to,
node dot value. Yeah, sorry, missed that one.
You might need to, if you want to make those a tuple, you might need
thank you. Let's do this so that it's easier for everyone to see. I'm going to do it as, how did I want to write this? Yeah, the tuple, thank you for that. Okay, so just so you can see it again, I'm going to write on top. So it's going to be node, parent, grandparent. You guys see that? So then I'm just moving it over a bit. And so I'm going to append this and it's going to go through it. I'm going to do the same thing for node dot right.
Just to make sure, wouldn't you do parent dot value?
Value. I'm trying to think about how I'm adding parent.
You're showing on line 17 that grandparent that should be a value.
I think it would just be parents because parent will be pulled from node dot value already. Yeah. And so it would already be a value.
Oh, I see. Okay.
So I'll write that though, because that is not clear that I am doing that. So let me put that. Parent is already set to dot val. That is why you do not need to use dot val when you pass it. Dot val when you pass it as a grandparent. Okay, is that clear the way I wrote it on lines 32 and 33?
Yeah, totally.
Cool. Okay, so let me see. I think we're almost done here. So let's see. Did I do? I might be missing an if. Okay. Not root. Let me look at my constraints here. They said there should be a root. Okay. Let's run the code. I'm sure there's going to be things that I have not. Grandchildren sum. The D again. Oh man. Maybe it's my keyboard. Grandchildren sum again. Oh man. Yeah, maybe it is my keyboard. The D doesn't like me. Okay. So you can see right now that this is still passing for that. Let's first verify that it passes for everything else. Okay, cool. It passes for that. Awesome. Alrighty, so let's now look at what it does. This is a lot of information, and if it's your first we might even have time to do the other one if you want to see it. Questions on this so far? The other one also uses a similar style to what I have on lines 14 through 19. But this is basically how it will look like for DFS. You will get all the initial values. You'll figure out what those initial values are. You'll put them in a stack, and then you'll iterate through the stack accordingly and append to it whenever from the description you'll get, okay, append in this case.
Great. And yeah, I just want to be respectful of your time and volunteers' time. Thank you so much. I'm going to clap. Yeah, and for people watching on the YouTube, this was Krys Flores. We'll leave a couple links in the video description to where you can find her on the internet and the problem statements and all that. Thanks everyone for attending.
Thanks, Elaine.
Thanks. All right, I'm gonna stop recording.